Did you know that the Milky Way has a warp in its outer disk? Well, you've come to the right person to find out more about it. I'm Seti. I'm a PhD student studying the Milky Way and in particular the galactic warp, and today we're actually going to be talking about it. So I prepared a really nice short and sweet presentation covering a lot of basic aspects about the warp and, more importantly, my own work that I've been doing over the past year, contributing to, I guess, all of the knowledge that we have on the warp. So without further ado, let's just jump right into it. So I think most people know this, but the Milky Way is actually a barred spiral galaxy. And this isn't necessarily a very unique thing. I think quite a lot of galaxies in the universe are barred spirals. So there's nothing really special about it from that aspect. What people don't really know is that spirals are what we call kinematic density waves. And this is essentially like traffic jams of stars. So where stars sort of bunch up in certain places. And that's what then creates these really interesting and unique spirals. What's really cool is that these spirals are actually mainly formed in the gas within the disk of the galaxy, and when you get compressed gas you get a lot more star formation and young stars, and so that's why a lot of spiral galaxies tend to have very bluish arms, is because the gas is recently compressed and created a lot of baby stars who haven't really travelled outside of the spirals yet. But what's really important is that while in a couple cases a lot of these spiral galaxies are, well, their actual spirals are in some ways a little bit corrugated, maybe a bit bumpy, they're not typically expected to be that, and they're not mathematically so, at least. And in general, spirals are confined to the disk plane, so they don't really corrugate or bump up and down. Instead, the Milky Way actually has a very unique vertical feature, which is a galactic scale warp. And you can actually see this in the image at the bottom here. It's sort of like an S-bend, and it mainly affects the outer regions of the disk. So we're talking about roughly like 9 to 12 kiloparsecs outwards. So what's that in light years? I think that's like, if you multiply it by 3, that's about 30 light years from the galactic centre, so a little bit further out from the sun's radius. And it's actually seen in quite a lot of other disk galaxies. Sanchez Saavedra, I think they have surveyed quite a few like northern hemisphere disk galaxies in the 1990 paper, although they also published a paper in I think 2002 or 2000 focusing on southern hemisphere galaxies, and I think most of them actually showed signs of a warp in the galaxies where the disk was actually visible. But let's look at the warp in a little bit more detail with the maths. Now, you don't really have to understand what's going on with this in complete detail, but it is important for me to sort of build up your own knowledge on this. So a bit similar to the kinematic density waves, we consider the warp to be what we call a bending wave. And so instead of areas where the density sort of clumps up and gets really high, it's actually like the height of the stars go up and down like from the disk. And typically speaking, we would actually formally represent it with what we call sine waves, so sinusoidal waves, so up and downy waves. Within the Milky Way, it's the m=1 mode, so that is where one side of the disk is up and one side of the disk is down. That is the most important one, and you can actually see it in this really handy image from a paper by Shen et al. And this is where they use a lot of baby stars, so Cepheids, really young stars, and they map them out around the disk, and you can see it in that image there, and they sort of create that S-bend warp. We also know that the disk, well, the warp starts at around about 9 to 11 kiloparsecs in radius, so the innermost regions of the Milky Way are actually flat. And well, we don't really know exactly where it starts, so Chen actually estimates it starts at around 9 kiloparsecs, but Denon suggests it's around 11 kiloparsecs, so we're a little bit uncertain with that. And it doesn't necessarily have to be sort of stationary or unchanging with radius. You can have it sort of twist around into a spiral, a bit similar to the density waves as well. And we can represent this pretty simply with this equation at the bottom over here, which basically has the amplitude, which is A, which is going to be a function of the radius minus the starting radius. So that accounts for the fact that it's not going to be starting right from the center of the galaxy. And then we multiply that by basically a sine curve. And if we want to sort of shift it with respect to the sun, all we need to do is minus it by an angle called the line of nodes. And that line of nodes is where the warp hits the midplane, so where it actually crosses the flat part of the disk, essentially. We can also sort of expand this a little bit more, because when we look at sign fits, or the sign fits that we've just talked about, usually we use them in the context of sort of observational sort of studies on the warp, and they tend to be a little bit more on the static side, but we can sort of broaden our model to, I guess, include like the velocity of the warp as well, which is quite an important part of it in addition to the positions of stars. So we can basically use a continuity equation. For this we use the collisionless-Boltzmann equation, the 0th moment of it, which basically tells us conservation of mass, and we can adapt that to get this really interesting equation over here, which tells us the precession of the warp is equal to the azimuthal velocity, so that's basically the circular velocity of the stars divided by the radius. And then if we can model our warp, both the position, so the height of the warp, with the sine wave that we just discussed earlier, and also do the same for the velocity. If we take like the average of it, or even the maximum of it in this case, and divide one by the other, we can use all of this together to get basically an estimate for precession of the warp, which is quite interesting. So there are two main suspects when it comes to the warp. Now there's actually quite a few other ones which I won't get into today, but for the main one, well, the main two we think are companion galaxies to the Milky Way, and the main one is the Sagittarius dwarf spheroidal galaxy. I think it's also called the Sagittarius dwarf elliptical galaxy as well, but for brevity I guess we'll just call it Sagittarius from now on. This is probably one of the most close companion galaxies with the Milky Way. In fact, it had a very recent close encounter, we think was probably around like 300 to 900 mega years ago, so 300 to 900 million years ago, so very, very short, very, very close in terms of like I guess the age of the universe and like the actual age of the galaxy. And this was where it crossed the disk at around about 18 kiloparsecs. It's currently at around a distance of 20 kiloparsecs, so it's still very, very nearby to the Milky Way. And we know it fed a lot of stars and gas into the Milky Way, so it's shed a lot of its own mass, which is really important. Because the problem is when it's lost a lot of mass, it's very difficult to sort of work backwards and figure out how large was it originally. And that plays a really important sort of role in determining whether or not it was even big enough to make such a big impact. So it's quite a challenging sort of suspect to sort of figure out. And then of course, if it's so close and given its orbital trajectory, it might have had multiple encounters in the past as well. So we don't know if sort of, I guess, the big sort of impact that would have created the big warp that we see in the galaxy today. Was it created by the last encounter, or was that too short a time scale? Did it have to be a prior encounter when Sagittarius was even larger than we suspect it could have been? So a lot of questions and not very many answers. The second and slightly, I guess, less suspected suspect is the Large Magellanic Cloud, or the LMC. Now this one is much further away. I think it's around 50 kiloparsecs, although I can't really remember off the top of my head, but it is considerably larger. So when it comes to its gravitational influence, it's probably roughly comparable to Sagittarius. So like that's kind of the main argument for it being probably at least one of many components that are contributing to the warp. But the main question is, if it's so far away, has it sort of been at its proximity as it is now for long enough to actually be influential? Because these things take time. It takes time to develop a warp. So has it actually been in the right position for long enough to actually cause that? And we don't really know that just yet. So why should we even study the warp in the first place? Or why am I even interested in this PhD in general? Well, personally, I think it's really important in terms of understanding what's actually been going on in the Milky Way. It's very difficult to be able to suss things out and sort of basically do archaeology on things in astronomy because of how distant they are and how little sort of, in a way, it's very difficult to be able to infer things because of their distance and, you know, dust and things like that. I mean, there's a reason we kind of call the Milky Way sort of the zone of avoidance in observational astronomy, because we don't really want to actually be looking directly into it. But it is really important that we understand what's going on with it, so we can figure out what's actually been going on with the Milky Way throughout its history and its evolution to get it to where it is today. And it also can reveal to us a lot of things about like past and current mergers. One current one being, of course, Sagittarius, but a really notable past one being the Gaia sausage. And this was probably around 8 to 10 billion years ago, where another companion galaxy called the Gaia sausage, or Gaia Enceladus, there's like a couple names for it, actually completely merged in with the disk now. And we were able to figure that out using the kinematics of stars within the disk, and figure out that there were some that weren't really moving with sort of the general sort of motion of the disk. So we were able to figure out that these were all belonging to a prior galaxy. So very, very interesting stuff that we can figure out just from the kinematics of stars. Furthermore, I think it's also really interesting in understanding a little bit more about the potentials of galactic disks, not just the disk on its own, but in combination with the bulge of a galaxy plus the halo, because these all have very different potential profiles and density profiles. And it's really, really hard to estimate the potential for things like this. You have to do it numerically a lot of the time. So being able to understand sort of how masses and like companions can influence the shape of things can tell us a little bit more about how the density is distributed in the galaxy. And that's really, really important when it comes to building good simulations. And of course, I feel like I've touched upon this very, very briefly a couple minutes ago, but this is really important in its applications to other disk galaxies, because we can sort of see the Milky Way's stars and the disk best because we are in it in a way. So we can use that to our advantage to understand a little bit more about disks and of course their potentials, and then apply it onto other disk galaxies that are nearby. Right, let's actually get on to the main thing that I've been doing over the past year. So we're going to look at some of the simulations that I've been running, and I'm just going to quickly tell you a little bit about what they actually are. So for context, we've been looking at building simulations for which are looking at a single interaction with one very close by satellite. So we're making a scenario that's very similar to what could have gone on with Sagittarius and the Milky Way. For this, I used a software or a stellar library called Agama to basically build the initial M-body simulation. And I should also mention that it was a collisionless system, so we're only really looking at the stars within the Milky Way. We're not looking at the gas or the hydrodynamics. For this, we made basically a simulation that consists of a bulge, a disk, and a halo, and the majority of the mass is within the halo in the form of dark matter. I think about 99% of it was in dark matter. So kind of trying to recreate accurately the conditions within the Milky Way. And then in addition to the Milky Way, we of course have our Sagittarius galaxy. This was just modelled as a single particle. We call this a sync particle. And I ran 3 simulations. Well, I've now run 4, but for the context of today, we'll just talk about 3. And these all had varying masses. So for the first one, it was massless, so it was just the control simulation, sort of looking at how the galaxy is evolving in isolation. The second one was a low mass simulation, so I put Sagittarius's mass to be about 1 × 10 to the 10 solar masses, so times the mass of the sun, and that's a little bit more of a sort of lowish mid estimate for the Sagittarius dwarf spheroidal galaxy. And then we also have a high mass sim, which is on the higher end of estimates, which is 4 times that. Evolving the disk was done through a software called Ramses, which I won't get into for now, but basically all this does is it re-estimates the potential and moves the particles along. And these were run for about 3.5 to 4 gigayears, depending on the mass of the simulation. I hadn't realised at the time that if you have a more massive Sagittarius sync particle that the simulation doesn't run as long because it's more computationally challenging. But I have learnt my lesson now and I won't make that mistake again. So let's have a look at some of the pictures that I've got of our simulations. We're going to start off with the low mass simulation, and this time span is just sort of slightly after Sagittarius hits the disk and sort of causes a kerfuffle, basically. And you can really see, like, you can start to see a bending wave sort of emerge. So on the top row, we've got the, not Sagittarius, we've got the surface density of the disk. So this is where you're going to see those spirals and those density waves. In the middle row, we've got the bending waves, so the height above and below the galactic plane. So we've got pink being the positive height and then green being the negative height, so things moving up and down. And then likewise, we've got the same for vertical velocity on the bottom row. So red is going to be the positive vertical velocity and blue is going to be the negative. And you can see shortly after the impact, it basically creates quite a lot of interesting bending waves and uppy downiness and warps and stuff. And it looks really, really interesting. It sort of swept out quite a large amount of area in the outer galaxy as well. For the high mass sim, you get almost exactly the same thing, but things are sort of amped up a little bit more. So you can see the density waves are way stronger in the top row, and they kind of look a little bit like a grand design spiral galaxy, which is so pretty. You can also see more like stronger bending waves in the middle row and the bottom row as well. So things are warping much higher and much lower. So there's a really big contrast. And of course, it swept out an even bigger sort of radius, a bigger void of stars as well, which is really interesting. As for the control sim, we've got 3 images here that span for double the time span. So we've got just before it should have impacted the disk up to a gigayear, and you can see it really doesn't create such strong, I guess, spirals in a way. It's more flocculent or discontinuous, which is quite an interesting discovery. It's kind of what I would have expected, but yeah, it's quite interesting as well. But also you do get a little bit of warping motion as well shortly after the simulation starts, so that's quite interesting too. If we want to have a look at later times, we're looking at 3 gigayears after the impact. And for the control sim and the low mass sim, you can actually see a warp starting to form in both simulations. But for the high mass sim, you can sort of see that we get kind of like a flare, basically. So you can see that it's sort of not just all one side is pink or one side is green here. You can sort of see pink and green sort of mixed in with each other, which is indicative of quite a flare, basically. So some stars are really high above the disk, some stars are really low below the disk. So that's really, really interesting, and I did not expect that. But looking back at both of them having, both the control sim and the low mass sim having a warp, one interesting thing is that both the sims, so sort of looking at these more central parts of the disk, both the inner parts of the disk are experiencing a warp as well. And that's kind of wrong, because if you have like the entire disk is warped, that's kind of just a tilt. That's not actually a warp. First thing I needed to do was to kind of correct that and untilt the disk and see if there's still a warp. And indeed there was, so thankfully all of my efforts weren't in vain. And you can just do this by looking at the angular momentum of the inner disk. So I picked around 5 kiloparsecs, so a little bit closer to the center of the galaxy than the sun is. And it showed that there was a tilt of about 0.3 degrees per gigayear, which doesn't sound like a lot, but it does add up quite a bit in the grand scheme of things. So after untilting that, you can see this below in the plot below. This is for the low mass sim, that the inner part is less tilt warped, so it's a little bit more even, but the outermost regions actually shows a much clearer warp, which is fantastic. That's kind of exactly what I wanted. And the exact same thing happened with the massless sim, so the control simulation as well. The next thing we need to do is actually basically fit some sine waves to this warp. And so basically what the equation was for the height, so the amplitude multiplied by the sine wave minus the line of nodes, basically fit that, and then we can go on to basically figure out what's going on with the precession, if there even is one. So that's exactly what I did. I've got an example of this below me. We've got the height in the purple and then the vertical velocity in the green, and this is at 3 gigayears as well. And you can see that the stars sort of follow a roughly sinusoidal pattern. You've got a little bit of noise, and that's completely expected. And basically this is for the outer regions of the disk between 16 to 17 kiloparsecs, and that's where the warp signature is clearest and where both the control sim and the low mass sim experience a warp, and that's kind of important if we want to be able to compare things. But yeah, at around 3 gigayears, we can see that the amplitude for the control sim, well, which isn't pictured here, but I'll just tell you it, was about 0.24 kiloparsecs, so that's the height above the disk, the maximum height at this time for this radius. And then for the low mass sim, we got slightly higher at 0.27. And for the extremely high mass sim, if I remember correctly, we actually got something a little bit lower than that, but there are a couple reasons for that. Which I will probably talk a little bit about later. But in general, with that aside, in general, we see that more impact mass means that we get a slightly higher warp. So kind of reassuring in a way. Following on from that, we can use these amplitudes to then sort of fit a relationship for these amplitudes with respect to radius. So see how the warp is growing as we move further and further out of the galaxy. And once we do that, we can basically sub these into our continuity equation and get estimates for the precession, which you can see here. On the above, we've got the control simulation, so the massless simulation, and then at the bottom we've got the low mass simulation. And overall, it shows that the warp is mostly the precession is mostly positive, so that means it's prograde and it's moving with the stars. It's moving slightly slower than the stars, around about, it really depends on which part you look at with these graphs, but about sort of a third of the speed of the stars within the Milky Way for the low mass sim. So we're getting, at 3 gigayears, roughly around 11 to 12-ish kilometers per second per kiloparsec, which has been documented in other studies as well, so that's kind of reassuring. And then for the control sim, you get it overall a little bit higher. However, one interesting thing is that the control sim has a lot of these very repetitive and sort of repeated spikes, which is a little bit interesting. However, with the low mass sim, you can sort of see at the later times that you get a sort of period of stability, which hopefully is long lasting, but we don't quite know yet until we run the simulation for much longer. But yeah, overall it tends to be a little bit more prograde, which is as expected. And the spikes and dips are usually caused by times within the disk, within a certain radii where it's actually very shallow and there isn't much sort of sign of a warp. And when you have a very shallow fit, you can it can sort of vary quite rapidly and quite violently and vigorously. So you can get a lot of variation in the amplitudes and the line of nodes. So that can sort of fuzzy things a little bit more. And if things vary quite a lot, when you want to then go and fit any relationship, which I did using a MCMC or Monte Carlo Markov chain, it can sort of throw things off a little bit, so that's why we get those very odd spikes. So do any of the simulations actually match real life? This is a very tricky question to answer because there are a couple features within each simulation that kind of make it more preferable over another one, or some disadvantages they may have over others. So it's a bit difficult to sort of make a really sort of definitive judgment here. So for the high mass sim, you could get the warp height best. So without any of the sign fits, just looking at the raw data, the warp height actually reached around 1.2 kiloparsecs, which is actually comparable to what we see in the Milky Way. We expect it to be about a kiloparsec. Within a radius of 16.5 kiloparsecs. So that is kind of reassuring, but it needs a lot more bending wave modes. So you need a more complex model to be able to fit it, and we could kind of tell that with the flaring as well. So I wasn't able to get a very accurate analysis with that one, so more work would be needed with that. When it comes to the lower mass sim, it matches the shape pretty well. We get that really nice sinusoid that starts at around 9 to 10-ish kiloparsecs and then grows as we go further out from the galaxy. So that is really reassuring. But the warp is a little bit more weak than we would have expected. We would have hoped it would be about 5 times larger. So that's really not good. And then, of course, with the control simulation, it also has the same thing. But, of course, it's very shallow, even shallower than the low mass simulation. And of course, there's a lot more noise in it as well, you can see with those spikes. So whether or not there is a warp or not is kind of difficult to tell with that one. And also we know Sagittarius has impacted the disk. So it's not accurate just from a more fundamental viewpoint. So there is that. Another thing that we need to touch upon is the fact that Sagittarius impacted the disk less than a gig a year ago, the last time it did, so between 300 to 900 mega years. And so it's kind of difficult to say at what point of the simulation do we take as today, because that is quite a broad range. And I think the most important thing is that within this time range, all of the simulations, with the exception of the control simulation, experience a lot of turbulence and sort of aggressive and dynamic changes as it's evolving. So it's still very chaotic, and you can't really make any very concrete conclusions with anything at these time points. So it's really difficult to say, and one suggestion is that perhaps it was an even earlier encounter when Sagittarius was even larger than it was today. That could have been the definitive encounter that would have created the warp. And this isn't just suggestive in my own work, it's been suggested in other works as well. So that may actually be the case. It's hard to tell at this point. So I guess we should conclude. We've looked at 3 different simulations that I've been working on over the past 3 years that are sort of based on the Milky Way and a Sagittarius-like interaction. The mass of the satellite can very vastly change the dynamics within, the Milky Way and its evolution. And a simple sign fit can work for low mass satellites, but when it comes to much higher mass satellites, we really do need something a little bit more complex. And for that, we probably need something that's not bimodal, so one side's up, one side's down, but quadrupole, or quadmodal, I don't know what it's called, but it's basically split up into quarters, basically. And that, I think, would actually fit the high mass sim best. And for that, I could probably use Fourier decomposition for that, something different. So we'll go through some different sort of analysis much later on. But yeah, leading on to that, things I should really be working on next is working on an intermediate mass sim. Now, I have actually done that, and just to very quickly summarize it, we also get a bimodal warp. It actually warps way higher than the low mass sim. We get a maximum height and amplitude of around 0.45 kiloparsecs, which is double, well, almost double the lower mass sim, which is really reassuring, but not quite at the heights we would want it to match the Milky Way in real life. So that's really reassuring. But yeah, interesting stuff. One thing that I really should do is extend these simulations up to much greater time scales. So I'm talking at least 6 gigayears, ideally double, so 8 gigayears would be great, and we can sort of see if there is any sort of, I guess, long-term tranquility later on in the simulations. And then, of course, I think the most obvious leading point from that is to then look at a LMC type satellite, so something that's a little bit more distant but a lot more massive, interacting with the Milky Way, and see what kind of effects that has on the Milky Way's disk. And then eventually it would be really cool just to combine the two as well. That would be quite fun, but that's way down the line. I'll probably talk about that in a video in a couple years time. But yeah, that basically concludes my work. I've done a couple other things as well, of course, looking at the line of nodes specifically and how they move over time, although that wasn't as successful. But yeah, it's been really fun working on this PhD, and I'm really glad to have got some really funky plots and funky, really pretty pictures of my simulation as well. Makes it really rewarding to be able to see these kinds of things. But yeah, it has been absolutely fun. Now, my next video is going to be on my little phase spiral blanket. I am halfway done with all of the little squares and stuff, but oh my goodness, it is taking me ages, and with this heat, I just don't want to work. I just want to sleep. And probably following on from my probation review, so I'm going to give this talk tomorrow, I will probably have to nap a little bit and take another break. But yeah, with that being said, thank you so much for watching me, and thank you so much for joining me as I'm working through this PhD and listening to all of the stuff I have to tell you. It's been absolutely fun, and it's been a pleasure to have you join me as well. My voice is going, hay fever and allergies and stuff have, I guess they're taking over right now, and I need to save my voice for tomorrow. So I'm going to call it a day for now. Thank you very much for joining me. Stay hydrated, and I shall see you in the next video.